Let's take a look at the 8th question. In the figure, a container is shown to have a movable, that is without friction, piston on top. The container and the piston are all made of perfectly insulating material, allowing no heat transfer between outside and inside the container. The container is divided into two compartments by a rigid partition made of a thermally conducting material that allows slow transfer of heat. The lower compartment of the container is filled with 2 moles of an ideal monoatomic gas at 700 Kelvin, and the upper compartment is filled with 2 moles of an ideal diatomic gas at 400 Kelvins. Now, the question has two parts. The first part being, consider the partition to be rigidly fixed so that it does not move. When equilibrium is achieved, the final temperature of the gases will be what?
So let's write down the data here first, whatever we have. So in the upper one, we have a gas at 400 Kelvin, 2 moles, whose CV would be equal to 5 by 2R because it is diatomic. And the lower compartment, we have 2 moles with a 700 Kelvin, and CV would be equal to 3 by 2R.
Right.
Now let's see what kind of processes they might undergo. Consider the partition to be rigidly fixed so that it does not move, which means that this gas will be confined to this particular area only. Hence, for this particular gas, it would be a constant volume process.
Right.
While when the equilibrium is achieved, the final temperature of the gas. But nothing is said about this piston. Since at the question it was given that it is movable, so it has to be in, like, the pressure on the outside will always be same as the pressure on the inside.
Right.
And so for this it would be a constant pressure process. So using these concepts we move on, and one thing more we note is that it is completely insulating and no heat transfer between outside and inside of the container.
Right.
So whatever heat this would give, only the upper compartment can take, and vice versa. So since this is at the higher temperature, we expect the temperature of this to increase and this to lose its heat. Now let's see how that will happen. It will happen by a constant volume process.
Right.
Therefore NCV delta T would be equal to 2 into CV is 3 by 2R whole into 700 minus T.
Right.
Now this is the heat lost by lower compartment. And the heat, this would be same as the heat taken by the upper compartment, but because that will undergo a constant pressure process, we have to write for that as N Cp delta T would be equal to 2 into 7 by 2R.
Right.
We get this 7 by 2 as we know Cv is 5 by 2R and Cp equals Cv plus R. So we just add an R whole into we get T minus 400. So equate them both. We get 3 into 700 minus T would be equal to 7 into T minus 400.
Right.
We get the value of T to be equal to 490 Kelvin.
Right. Okay, so we'll move on to the next part of the question now. The next part says that now you can consider the partition to be free to move without friction, so that the pressure of gases in both compartments is the same. Now total work done by the gases till the time they achieve equilibrium will be.
Now see, in this question it is given that consider the partition to be free. So basically the partition can also move now, but without friction, so that no undesirable energy losses are there. So the pressure of gases in both compartments is the same. And since the piston was also movable and in equilibrium with the inside, so we can say that this pressure would be equal to the pressure on the outside.
Okay.
Hence, by this statement, we have proved that for both the processes, both the compartments, the process would be constant pressure.
Right.
hence an isobaric process.
Mhm.
Now let's find the total work done by the gases till they achieve equilibrium. So we consider the gases, say delta W1 plus delta U1 would be equal to delta Q1,
Right.
which would be the heat lost by 1,
Mhm.
and delta W2 plus delta U2 equals delta Q2, which would be equal to the heat gained by 1. Since there is no interaction between them and the outside environment,
Right.
hence we have delta Q1 plus delta Q2 would be equal to 0.
Right.
And in this case, what can we write delta Q to be? So in this case, we can write them to be N Cp delta T1
Right.
plus N Cp delta T2. These are equal to 0 because basically these are constant pressure processes.
Right.
And for constant pressure processes, we have delta Q equals Ncp delta T. Delta T1 is the change in temperature for the first gas. Delta 2 is for the second gas.
Right.
And this is because the pressure would be the same during both the processes. So we have a Cp basically as both the moles were 2. So we just start off with Cp 5 by 2 into R whole into T minus 700 plus 7 by 2 whole into R whole into T minus 400. Now let's see. Well, we might think that here we can replace it by 700 minus T, but
Right.
we have to find delta T. We are not concerned with the magnitude of delta T.
Mhm.
So delta T is basically the final temperature minus the initial temperature.
Right.
So that here we won't write 700 minus T
Right.
because we have written down the equation. Whatever the sign would be, we'll get that.
Mhm.
So what we had written down T minus 700 was correct.
Right.
We don't have to get confused there. So using this equal to 0 because the net heat given and heat taken would be the same and their sum would be 0.
Right.
So this T comes out to be 525 Kelvin.
Right.
Now we see that the total work we have to find. So in our case we have delta U1 equals N CV1 whole into delta T1. This is basically because delta U is the state function. So we can just relate it with V and write NCV delta T.
Mhm.
This comes out to be 2 into 3 by 2 whole into R whole into 525 minus 700.
Right.
And delta U2, which is the change in internal energy for the upper compartment gas,
Mhm.
would be N CV2 delta T2
Mhm.
would be 2 into, this is CV not CP, so 5 by 2 R
Mhm.
whole into 525 minus 400.
Right.
Now we see, we'll just name these equations as equation 1, this as equation 2. Now we see here that when we add these two equations, we get delta W1 plus delta W2 plus delta U1 plus delta U2 equals delta Q1 plus delta Q2,
Which
would be 0.
Right.
So with the help of this, if we know delta U1 plus delta U2, we can actually find delta W1 plus delta W2,
Correct.
which is the sum of the work done by them, which is which will be the total work done.
Right.
So we have delta W1 plus delta W2 would be equal to negative of delta U1 plus delta U2. So by doing these calculations and adding them up, we get it as minus of 100 R which is equal to our work done.
Alright, we'll move on to the next question now. Let's take a look at the ninth question now. A thermodynamic system is taken from an initial state I with internal energy Ui equals 100 joules to the final state F along two different paths IAF and IBF as schematically shown in the figure. The work done by the system along the paths AF, IB and BF are denoted by WAF, which is 200 joules, WIB, which is 50 joules, and WBF, which is 100 joules respectively. The heat supplied to the system along the paths IAF, IB and BF are QIAF, QIB and QBF respectively. If the internal energy of the system in the state B is UB equals 200 joules and QIAF is equal to 500 joules, the ratio QBF by QIB would be what? Prasoon will tell us what it will be.
So this is a diagram basically in which we see that the initial state and the final state are the same, but two different paths are used to reach it.
Right.
So we can get that delta U would be the same because these are the same final path, same final position they have reached for starting from the same initial position. So to basically get to the data, to basically use the data, let's draw a particular chart so in which we can represent all the data effectively.
Right.
So let's do this by this method. We are drawing this. In the first column we have our process. In the second column we have the work done in that process. In the third column we'll have the delta U, or the change in internal energy, and in the last one we have the Q, or the heat supplied.
Okay.
So this two we divide in two halves. So first we have our process IA, and then we go from A to F, so AF.
Right.
And we have a process IB, and then from B to F. Now note, if we combine these two processes, we'll have the same. We'll have to go to the same process IF. That is, we go from I to F through this process and then to this process.
Right.
These are two paths basically.
Correct.
So for IA, let's see if we can find out the work done. See, IA here is a constant volume process. Hence, we can actually get the work done should be equal to 0. Delta U we are not given, but Q it seems that we have been given, and Q for both of these is given out to be 500. Okay.
Right.
Now we go to IB. Let's see, before going to IB, let's check for AF. WAF is given for 200 joules, so we write that down, 200 joules.
Right.
Delta U is not given, no other data is given. Now let's check for IB. We given the work done at IB as 50. For BF we are given it to be 100. And the delta U here is given out to be 100. Now why so? Because UB is 200 and we know that UI is 100. So UB minus UI will give the change in the internal energy during that process.
Correct.
So that we have got by 100. Okay, so now let's see what we can do here. Now if we find delta U, let's see, we can find delta U because for this process, for the process IAF, in going from I to A to F, we have the total work and we have the total heat. Hence, we can find the total change in internal energy for this process.
Right.
So let's find that. We get Q equals delta U IAF, delta U IAF plus total work IAF. So basically we have QIAF is 500 equals delta U IAF plus the total work IAF is 200. Right. Hence delta U IAF comes out to be 300 joules.
Right.
So basically we can now get UF, which would be equal to UI plus delta U IAF, because this process was from I to F and we add that to I, so we get a UF. So UI was 100, we get this as 400. Now let's see one more interesting thing. Here we have the delta. Now let's see what else we can find through this. Delta U from I to B is 100. So let's take a process I to B and then B to F.
Right.
So delta U from I to B is 100. We are considering delta U here. B to F we don't know. But for this total process we know the delta U, which is 300. Hence we can find the delta U for the process B to F also.
Right.
So delta U IB plus delta U BF would be equal to 300, which would be equal to delta U IF as we had seen. So delta U BF would come out to be 300 minus 100, which is equal to 200.
Correct.
So here we can write down 200. Now let's see what we are asked. We are asked to find the ratio QBF by QIB. So QBF by QIB. Now since we have W for them, both of them, and delta U for both of them, we can easily find them by just adding them up. So Q equals delta U plus W, our basic formula. We apply that for BF and we get QBF equals delta UBF, which is 200, plus work done in BF, which is 100, equal to 300, and we apply that for IB.
Right.
So QIB would equals this, our delta U is 100, plus work done, which is 50, equal to 150. Hence QBF divided by QIB would give us 2.
Okay guys, so we have another solution for us here. We'll see what happens in the next question. Now, the 10th question of kinetic theory of gases tells us that there are 3 curves that are given to us. One of them is isothermal, the other 2 are adiabatic, with gamma 1 being more than gamma 2. Identify them. Prasoon?
So basically we have these 3 curves, and at this particular point we see they are going through the same point.
Right.
So we have to find the slope. For that we'll need their particular differential equations. And when we get the differential equations, because these 2 terms are the same, we'll just substitute let's say the values at these will be P0 comma V0.
Correct.
So, or basically because P is on the Y axis, so it should be V0 comma P0.
Correct.
We'll just substitute them and see and compare the slopes. So first we have an isothermal process for which PV equals nRT, or PV equals constant. So let's just differentiate it with respect to V. So dP into V plus V dP equals 0.
Right.
We have to find dP by dV, which would give us the slope. So
this is for the isothermal process, right?
Yes. We just made a small error here. dP into V plus P into dV would be 0. Hence dV dP by dV would be equal to dP by dV
minus P by
minus P by V.
Right.
Okay.
Yeah.
So this is been obtained for an isothermal one. We can just substitute for that particular point P naught by V naught, so minus P naught by V naught.
Right.
Now we have an adiabatic process with PV to the power gamma equals constant. So we differentiate it and see what this will amount to. So P gamma V to the power gamma minus 1 dV plus dP V to the power gamma would be 0.
Right.
And we would get dP by dV as minus gamma P by V, and on substituting them by P naught and V naught, it would amount to minus gamma P naught divided by V naught.
Right.
So now we can just compare. dP by dV is just the slope. Okay. So let's just compare. By seeing it, we can say that the magnitude of C, the slope of C, is more than the magnitude of slope of B, is more than the magnitude of slope of A.
Right.
So we take mod dP by dV. It comes out to be P naught by V naught for isothermal, then gamma 1 P naught by V naught, then gamma 2 P naught by V naught.
Right.
Now we find the one with the least slope, because gamma, we had the formula for gamma equals 1 plus 2 by F. So for this, it will always be greater than 1. Hence these two terms, gamma 1 and into P naught by V naught and gamma 2 into P naught by V naught, will always be greater than this one.
Right.
So for our isothermal part, since this is the least slope, A is our isothermal one.
Right.
Isothermal. And since we had that gamma 1 is greater than gamma 2, so the slope of the one with gamma 1 would be greater than the one with gamma 2.
Right.
And for that, we can write basically that B and C are the isothermal processes. BC are adiabatic processes.
Yeah.
And C has the maximum slope. So
Right.
C corresponds to the one with gamma 1 and
Right.
B with gamma 2.
Sure. So can you show us on the graph?
Yeah, let's just write it down here also. Now see this one, adiabatic process with gamma 1, which was the max one.
Right.
B is adiabatic process with gamma 2, and A with the least slope minus P naught by V naught is our isothermal process.
Right. So guys, we have found a solution to another question. Let's see what happens with the next one.